Good morning, good afternoon, and good evening. Thank you for joining us today. My name is Herdani Camacho, and I will be the moderator for our presentation. I am part of Fluor's Office of Technology, which focuses on using science and innovative engineering technology to build a better world. Our engineers, designers, and experts, in other words, our people, are at the core of our success. Today's webinar is titled Mitigating Loss of Containment Events Through an Integrated Risk Assessment Approach. Process safety is paramount in industries dealing with hazardous fluids. Containing these fluids within process systems is critical to preventing accidents and protecting personnel, the environment, and assets. Loss of containment, or LOC, incidents can vary from minor leaks to catastrophic failures, each with different consequences and frequencies. In this webinar, Fluor Fellow Veronica and subject matter expert Oscar Schot delve into an integrated risk assessment approach that addresses the full spectrum of LOC scenarios. The primary objective is to help the audience understand the different risk assessment tools typically employed in EPC projects, including their objectives and limitations. By combining various risk assessment tools, EPC project teams gain insights into the effects of different events and develop more thorough and robust risk reduction strategies. We explore how these assessments contribute to preventing and mitigating incidents in operating facilities. Nikhil, welcome to the webinar, and thank you for presenting the HSE topic. Over to you.
Thank you, Herdani, and good day, everyone. For our HSE topic, I would like to briefly talk about the process safety, consequence-based versus risk-based assessments. But first, let us define process safety. Process safety is a disciplined framework for managing the integrity of hazardous operating systems and processes by applying good engineering, good design principles, and operating practices. It deals with the prevention and control of incidents which have the potential to release hazardous materials or energy, that is, loss of containment, which is the focus of our presentation today. Such incidents can cause toxic effects, fire, or explosion, and could ultimately result in serious injuries or, in an unfortunate event, fatality, property damage, lost production, and can have a detrimental impact to the environment. To assess the risk associated with the loss of containment scenarios, it is typical to perform quantitative assessments in addition to qualitative analysis, as it provides more detailed information which can assist in identifying the protection requirements of the facility. But before we dive into the differences of the two approaches, I would like to do a quick review of the definition of hazard and risk. Most of the time, they are used interchangeably, but their meanings are different. Hazard is basically a source of harm, and risk is a combination of the probability of a hazardous event and the consequence of that event. More on risk. Risk is a product of probability and consequence. Probability is basically the likelihood of an incident occurring, and consequence is the severity of the outcome following the release of hazard. It can be, say, if we are talking about impact to personnel, minor injury to fatality. Risk is a combination of the probability of an event and the consequence of the event. In layman's term, risk is the chance of someone or something experiencing a certain level of harm. The table in the screen provides a comparison of a consideration when we do consequence versus risk-based quantitative assessments. In terms of the type of representative release scenarios typically covered, for consequence-based assessment, more frequent releases are considered, which are small and medium leaks. consequences associated with these leaks are modeled, but no frequency analysis is performed. Based on the consequence modeling result, specialists will check if the consequence criteria is being met. For example, if the consequence criteria for emergency equipment is 15 kilowatt per meter square, and based on fire modeling, the emergency equipment is outside that contour, then no additional protection is recommended. As for the risk-based assessment, this will consider the full range of representative leaks, from small leaks to full rupture. Consequence modeling will be conducted for full range of leak sizes. Frequency analysis for all representative leaks are performed to determine releases, ignition risk, and the frequencies, etc. If the study is to confirm if additional protection is required against escalation risk, typically receptor needs additional protection if it is impaired in the frequency of 10 to the power minus 4 per year or once in a 10,000 year or more frequent. The impairment criteria, of course, depends per client to client. In summary, the table provides details of the differences in consequence-based versus risk-based assessment. In the presentation today, we will be able to have snippet on when these approaches are typically utilized. Now for the main presentation, I will turn it over to Oscar and Veronica. Enjoy the rest of the webinar. Thank you.
Good day, everyone. Thank you for joining us today. And thank you, Nikhil, for the HSE topic. To begin, let's go through the objectives of the presentation. Process safety revolves around keeping hazardous fluids inside process systems, or in other words, containing the materials. Loss of containment incidents, which are also referred to as LOCs, can range from a minor flange or pump seal leak to a catastrophic rupture of piping or equipment. Both the severity of these events as well as their frequencies can vary. Undertaking the right hazard and risk assessment enables the project team to examine the effects of the full range of LOC events and provide risk reduction measures to manage the risk associated with them. Each of these HSE assessments have their specific objectives and are tailored for specific leak size events. This presentation shares a holistic view of how the full range of LOC scenarios are covered by various hazard and risk assessments that we perform at Fluor. It aims to help you understand the objectives of different assessments Design HSE performs, as well as their scope and limitations. Today we will present a selection of HSE assessment methodologies, explain what they are, and to which leak sizes they apply. We will discuss hazardous area classification, process hazard analysis, layer of protection analysis, HSE input to facility siting and plot plan development, fire safety assessment, critical building risk assessment, and finally, quantitative risk analysis. As Nikhil explained earlier, risk is a function of the likelihood an incident occurs, together with the severity of its consequences. When talking about the risk associated with loss of containment events, the focus is on the severity of the consequences and the probability that these events occur. Every identified LOC scenario can be located on this risk matrix, as seen in the screen, based on the estimated probability and severity. High-risk events in the top right of the matrix are unacceptable, and therefore a lot of effort shall be made to reduce these. Reducing risk can be achieved by reducing either of the two components, the severity or the likelihood. The preference is to reduce the potential severity of an event and make the process inherently safer. For example, eliminating certain hazardous substances altogether or reducing the inventories. Now, if the potential severity cannot be reduced, the likelihood should be reduced. So for example, adding a PSV does not completely eliminate the risk of overpressure and subsequent vessel rupture, but they do reduce the likelihood that this actually happens. Based on historical data, smaller leaks are more probable compared to larger leaks. That pattern is observed in failure frequency data published in various industry publications used in frequency analysis. For example, you can see in the table in the top right that a leak in a pipeline is about 5 times more likely than a full-bore rupture. Similarly, in the bottom right, you can see that larger hole sizes are less likely than smaller hole sizes. So we saw that large leaks are unlikely compared to smaller leaks. However, if small leaks are not identified and left unfixed, these can escalate into bigger events with more severe consequences. This is also referred to as the domino effect. And therefore, hazard and risk assessments should also address small leaks to help prevent, reduce, or delay events from escalating into bigger events. Risk associated with process safety hazards need to be managed throughout the life cycle of the facility. Fluor, as an EPC contractor, is heavily involved during conceptual, basic, and detailed design, as well as during the construction phase of the facility life cycle. As seen in the middle of this graphic, several assessments are performed to understand the hazards and the risk associated with loss of containment events in our projects during the design phase. These assessments are also performed to determine the risk reduction measures or safeguards that need to be implemented in the design. Or how do we assess risk associated with LOC incidents in our projects? Remember, risk comprises the likelihood an event occurs combined with its severity. So first, it can be done mainly based on experience and engineering judgment. This is typically a multidisciplinary team exercise. Some of the tools we use employ a qualitative approach, such as PHA or process hazard analysis and hazardous area classification. A semi-quantitative approach can also be applied, wherein some of the risk parameters are quantified based on specialist or team's experience, and some calculation is undertaken to determine the frequency of the event. Layer of protection analysis, or LOPA, is an example. And finally, a fully quantitative approach can be applied, wherein the severity of consequences is quantified using consequence modeling, and the overall risk to personnel is quantified as the probability of a fatality per year. The Quantitative Risk Assessment, or QRA, is an example of such an assessment. As a quick summary of the introduction, we discussed the risks associated with loss of containment events, the fact that smaller leaks occur more frequently than larger leaks, and the use of risk assessments to facilitate the risk management process. Let's now move forward to discuss hazard and risk assessments we typically perform on projects. The first step in any risk assessment is hazard identification. This is a critical step in the risk management process since you cannot manage what you don't know. One needs to understand hazards associated with the substances and services at the facility. This includes identification of properties such as flammability and toxicity. Based on this hazard identification, one can determine which assessments are required to further understand consequences and risks associated with those hazards. The matrix you see in the screen is a sample tabulation of substances handled in a facility, including the hazard classification of each. On to the risk analysis step. This is a list of analyses we can perform on projects. In the next slides, we will touch upon their objectives, their scope and limitations, and what kind of leak sizes they are covering. Finally, we'll explain how each assessment helps in reducing risk to tolerable levels. Case studies are also shown to provide demonstration of how assessments are used in projects. The first assessment is the hazardous area classification. Hazardous area classification is a qualitative assessment performed if flammable substances are handled in a facility. It is a method of analyzing and classifying the environment where a flammable atmosphere may occur. The main purpose is to facilitate the proper selection of equipment and instrumentation to avoid ignition of potential releases of flammable material. This original scope of the analysis was electrical equipment only. It is now extended to also include non-electrical sources of ignition like hot surfaces and mobile equipment. We do this assessment to support management of ignition risks, considering the most likely leaks or flammable atmospheres present. Hazardous area classification starts by listing all substances handled at the facility and their flammability properties. Then, all sources of flammable releases are listed, such as vents, rotating equipment, and valves, as well as the type and extent of the classified area. Finally, a hazardous area classification drawing is prepared, which provides a graphical representation of the classified areas where flammable vapors may be present. This drawing is then utilized to properly select equipment and instrumentation appropriate for the type of flammable atmospheres. Different codes and standards exist that can be utilized in determining the type and extent of classified areas. A few examples are the American Petroleum Institute, API, the National Fire Protection Association, NFPA, and the International Standards Organization, ISO. But other locations could have their own local standards. Do note that per these standards, it is stated that major or catastrophic loss of containment events are not considered in this assessment. And therefore, in terms of leaks being considered in determining area classification, we consider fugitive to small leaks only for area classification. The assessment aims to minimize the ignitions of the most likely leaks in your facility. Then, the next assessment is Process Hazard Analysis, or PHA. Process Hazard Analysis is a structured, systematic examination of a process in order to qualitatively identify and evaluate risks. It helps determine if risk reduction measures or safeguards are sufficient to control the risk. Typical PHA methodologies used are HAZID, or hazard identification, the what-if review, or a checklist-based review, and the hazard and operability, or HAZOP review. So although several PHA methodologies exist, we will focus on the HAZOP methodology today. This slide shows a typical flowchart of a HAZOP analysis, and part of the assessment is to determine the consequences of a deviation from the design intent, the risk ranking, and a listing of the existing safeguards, as well as providing recommendations in case risk reduction measures are insufficient to reduce the risk to tolerable levels. What can be seen in this screen here are worksheets from HAZOP sessions. Although the assessment is qualitative, depending on the deviation being analyzed, the leak considered can be a minor leak or it can be all the way up to a catastrophic leak. Both these examples here talk about overpressuring scenarios. Case 1 describes a limited and gradual pressurization of around 2 times the design pressure. With this limited pressure difference, typically only small to medium leaks are expected. However, since this specific scenario involves hydrogen sulfide, a highly toxic material, it was still considered a potentially fatal release. The second case describes a sudden pressurization of more than 5 times the design pressure. Equipment and piping systems exposed to such overpressure are typically assumed to rupture catastrophically, with potentially multiple fatalities as a result. And hence, based on the example provided, HAZOPs can cover all potential leak sizes, from minor sea leaks all the way to full-bore ruptures. The next assessment is Layers of Protection Analysis, or LOPA. LOPA is a simplified form of a semi-quantitative risk assessment that uses order of magnitude categories for initiating event frequency and independent protection layers. It calculates the frequency at which the event occurs based on the assumption that an initiating event should occur while also all independent protection layers fail simultaneously. Because if one safeguard functions, the incident is prevented. Additional layers of protection are allocated based on the amount of risk reduction needed to fill the gap between the calculated frequency and the risk target, as you see in this figure. So the concept is that there is this risk associated with the scenario, and it needs to be reduced to an acceptable level. IPLs will be applied to reduce the risk to meet this level. This is an example of a LOPA calculation. The event frequency calculated exceeded the target likelihood TMEL of the event, and therefore additional independent layers of protection need to be added. LOPA takes input from the HAZOP review that we discussed earlier. The criteria to determine which HAZOP scenarios need to be subjected to LOPA is determined by our clients. This slide shows an example of the selection criteria. As you can see, the scenarios being assessed in LOPA are associated with high risk and severe consequence events. And therefore, LOPA covers larger leak sizes which can result in severe consequences, typically ranging from medium-sized leaks to full-bore catastrophic ruptures. And for the next assessments, I will turn it over to Veronica to further discuss.
Thank you, Oscar, for covering the first three assessments. So to continue, let's discuss the assessments we perform to provide input to facility siting in plot plan development. In the screen is a picture of an aftermath of an explosion wherein neighboring communities were impacted. The primary objective of providing HSE input to facility siting and layout development is to prevent this from happening, and that's by arriving at a layout that minimizes both the risk associated with the overall facility as well as the risk to neighboring communities. HSE input in layout development implements inherently safer design concepts, one of which is the concept of segregation. The objective is to ensure that the hazardous facilities are located with sufficient distance from the critical targets on site and sufficient distance from off-site population and other off-site sensitive receptors. In addition, plot plan is developed to minimize the risk of escalation of events through the provision of adequate separation distance between adjacent process units. When selecting the location for a facility, one of the typical safety considerations is the impact of the facility to receptors external to the plant. Acceptability criteria comes from local regulations and applicable codes and standards, and they are often expressed in consequence-based and risk-based terms. As for determining plot plan spacing requirements, lookup tables are available, and these are available through local regulations, client standards, industry practices such as PIP or process industry practices, and other industry references such as what we can find in a CCPS book or Center for Chemical Process Safety book. In some cases, we also use insurers' requirements, such as what you can see on the screen, that is from Property Risk Consulting Guideline, which is previously known as GAP Guideline. However, we have to note that when we use these lookup tables, it only provides spacing requirement considering fire effects and does not cover blast and toxic release impacts. So to address this, in some projects, we conduct modeling of these scenarios and typically consider small to medium-sized leak. In the slide is an example of a facility siting using consequence-based results. An example of an acceptability criteria is shown in the screen, and this is based in an industry standard. The consequence modeling results shown on the table at the lower left is considered representative medium-sized leak. And as you can see, the consequence-based criteria from the industry standard is not being met, as the extents in the red font goes beyond the isolatable section distance to the boundary. So for example, if we take isolatable section 01 or IS01, it is only 61 meters away from the boundary, but the pool fire radiation extent is 99 meters. So therefore, the equipment belonging to IS-01, which is associated with pool fire, will have to be moved further from the boundary to make the facility siting compliant with the industry standard. This next example shows how facility siting uses risk-based results, say from a quantitative risk analysis or QRA. So what you can see on the right side of the screen is an example of an individual risk contour from a QRA, which is used to communicate the risk associated with the facility. So the risk is expressed in individual risk per annum or IRPA, or risk of something happening to a single individual for a year. So this is usually expressed in terms of frequency of fatality per year. So if an individual is standing on the red circle in the middle, and that is the 1E negative 5 per year contour, the frequency of fatality for that individual is 1E negative 5 per year, or 1 in 100,000 years. You can also observe that there are some facilities that are shown within the 1E negative 7 per year contour. However, this area is part of an industrial complex. So the facility siting is still compliant with the criteria, as it indicates that industrial complex can be within 1E negative 7 per year contour. So these contours that you see on the right side is generated considering the risk associated with full range of leak scenarios from the facility. So in terms of where these assessments fall into the graph, for consequence-based determination of the separation distances required, this considers most likely events. That's typically up to medium-size release scenarios. However, for risk-based approach, that's applied mainly for facility siting, all release scenarios are considered in the assessment. Fire safety assessment is the next on the list. So we do fire safety assessments on projects to confirm adequacy of the active and passive fire protection systems provided. So fire safety assessments can be done qualitatively, meaning the protection requirements are based on the review of the service classification, the applicable codes and standards, as well as the protection philosophy for the project. So the main intent of this assessment is to control the initial event to prevent it from escalating severe event. Therefore, the scenario considered are those that are from most likely scenarios, again, the small to medium-sized leaks. If the project intends to apply a scenario-based fire protection system, consequence modeling results can be used to confirm the design basis of the fire protection system. Similarly, this will typically only consider up to medium-sized releases, as the fire protection systems in most cases are not designed for worst-case events. However, it is also not uncommon to use risk-based approach where full range of leak cases are considered. This is typical in offshore facilities and sometimes also applied onshore, for example, determining the passive fire protection required against jet fire events. This shows an example of a fire hazard equipment list that we prepare for projects, and it is sometimes called qualitative fire hazard analysis. And the process of preparing this employs qualitative approach, wherein the entries are based on project protection philosophy and understanding of the fire risk associated with the substances being handled, while also considering the operating parameters. So the main objective is to prevent event escalation. Therefore, it considers most likely but low severity leaks. This analysis determines the fire protection which will be provided for the equipment and hence for the facility. This slide provides an example how fire water system sizing can be based on fire scenarios. So this case study is for a brownfield project, and the whole area that you see on the snapshot on the right side is within one fire zone. So in practice, fire water demand requirement considers a fire in one fire zone at a time. So following that concept, the fire water demand requirement for the whole fire zone results to a capacity that is more than what the existing fire water system capacity can provide. So to optimize the fire water requirement, consequence modeling results based on medium-sized leak was used to determine the highest fire water demand requirement for the facility. The circles you can see on the figure represents the area wherein high radiation from a fire is expected. Say, if you have a fire from sub-fire zone 3, the active fire protection system on the equipment within the circle needs to be activated. This enables a project to use fire scenarios from each sub-fire zones to determine the fire water demand the fire water system is required to be designed for. So doing this, the resulting fire water demand came within the existing fire water system capacity. So in terms of fire safety assessment, if consequence-based assessment is applied, it will typically consider small to medium release scenarios. And the main focus is preventing escalation of small releases to become larger events. In case in a project, risk-based approach is in determining protection requirements are to be implemented, this considers the full range of the release scenarios. To continue on with the list, the next is the critical building risk assessment, which evaluates the risk to critical buildings. So occupied buildings are the typical receptors considered in this assessment, wherein risk to personnel who spends time inside the building is evaluated. But there are also some cases wherein there are buildings that are housing critical equipment, such as those used for emergency purposes or those that needs to continue to function during the emergency event. So those buildings housing that critical equipment is also considered in the assessment. API RP 752 recommends 3 approaches which can be utilized in performing the assessment. The first approach is the consequence-based assessment, wherein typically we consider small to medium-sized leak. And then the use of quantitative risk assessment results, wherein all leak scenarios are considered. And then the use of spacing table. But again, this is only considering the fire impact. In this slide shows results when consequence-based approach is applied for evaluating explosion impact to the buildings. Explosion modeling is performed, typically considering the second approach shown in the slide. It assumes a congested volume is filled with flammable gas, which considers worst-case catastrophic leak. So to simplify the assessment, buildings are grouped per type, and then the impairment criteria is assigned per group. And then the explosion results are used to cite buildings according to their building type. So in this example, administration and maintenance workshop buildings are of B2 type, and B2 type is a steel frame with metal siding with critical overpressure used typically around 1.5 psi. As for the control building and substation, they are of B5 type, and B5 type is a blast-resistant building with critical overpressure of around 4 psi. So as shown in the results on the right side, the location wherein most of the buildings are sited are outside their critical overpressure contours. So for example, if we look at the administration building, It has a critical overpressure of 1.5 psi, and it is outside 1 psi contour. So that means that the overpressure load that is expected on that point is below 1 psi. Therefore, it is designed and considered sufficient to protect the personnel or equipment within it. It is also typical in determining blast loads to design for to consider risk-based results. And that's through the use of the exceedance curves, as you can see on the screen. An exceedance curve plots the side-on overpressure, which is on the horizontal axis, against the cumulative frequency of when this value is exceeded for a specific target. And that you can see on the vertical axis. The typical criteria considered for critical buildings is that they need to be designed for explosion loads from events with frequency of 1e-4 per year or more. So these results are generated considering leaks from full range of hole sizes. So for example, if we take building 8, the side-on peak overpressure is around 40 millibar. So this will then be checked against the overpressure that building 8 can withstand to confirm if redesign or structural strengthening is required. So for CBRA, as the receptor being protected is most of the time occupied buildings, even if the approach applied is consequence-based, worst case scenario is typically considered specifically for explosion events. For fire and toxic releases, up to medium-sized releases are usually considered. For risk-based approach, since it uses QRA results, then it will be covering full range of release scenarios. The last assessment which we will be covering is the quantitative risk analysis or QRA. So QRA is a technique used to systematically calculate the risk from hazardous events. This slide depicts the main steps involved in performing a typical quantitative risk analysis. It starts by identifying scenarios which needs to be considered based on the substances processed and handled in the facility. And then frequency assessment is carried out to determine the frequency at which a release of a hazard may be expected to occur. In parallel, consequence assessment can be done to predict the size of the consequences associated with the hazard. So for both steps, frequency assessment and consequence assessment, full range of leak sizes are considered. Results of these steps are then combined to quantify risk to personnel. So usually in terms of risk of fatality. So the results are then compared to the tolerability criteria, either set by local regulators or applicable codes and standards. So mainly the QRA results provide information if the risk level of the facility is within the range of what is considered tolerable by the industry. If criteria is not met, sensitivity analysis can be conducted to see how changes in input parameters can impact the results, or recommendations for additional risk reduction measures are made. So it also informs the operator which part of the facility contributes most to the risk, enabling them to align planned risk reduction efforts. So this is one of the example of the QRA output. You've seen that earlier already on the facility siting slide, but to reiterate, this is an example of a local location specific in this individual risk contour. So it provides information of a risk for an individual who is located at a certain location for 24 hours per day and 365 days per year. So again, if an individual is standing on the red circle in the middle, which is 1E negative 5 per year contour, the individual risk of that person is 1E negative 5 per year. So for QRA, it will cover full range of release scenarios. So to recap, what leak scenarios are being covered by the risk assessment we have discussed in this webinar. So hazardous area classification covers mainly fugitive emissions and small leaks. HAZOP, which is a qualitative assessment, could cover whole range of leak scenarios. For LOPA, because of the criteria being used to determine which scenarios will undergo LOPA, it considers medium to catastrophic leak scenarios. HSE inputs to facility siting and plot plan development, as well as fire safety assessment. It depends on the approach being applied. So it can consider up to medium-sized leak only or can cover the full range of the leak scenarios. For CBRA, for explosion impact to buildings, usually we consider up to worst case events because, again, we're looking at an occupied building most of the time. But for fire and toxic release events, the leak scenarios considered depend on the approach utilized. And then finally, for QRA, full range of leak scenarios are considered. So to sum up the main points that we would want to convey in this presentation, as part of the risk management process, hazard and risk assessments are required to provide detailed information to aid understanding of what can happen in case there is a loss of containment event and if they are not properly managed. This allows the project team, together with the operator or our client, to determine appropriate risk reduction measures required to manage risk to tolerable levels. Undertaking combination of several risk assessments enables the project team to examine effects of full range of LOC events and enables us to develop more thorough and robust risk reduction strategies. So the figure you see on the right provides visual summary showing that assessments are tailored to a certain type of leak scenarios and events. And it is important to understand limitations of these assessments so as to ensure that the right assessment is performed where appropriate. And finally, in deciding which assessment need to be performed for a facility, these assessments chosen should be aligned with the facility type and how risks associated with them are understood. In projects we perform in Fluor, we work with our clients to determine which assessments are appropriate for the project. So that brings us to the end of the presentation. We are open to any questions that the audience may have. Back to you, Jardani.
Thank you very much, Oscar and Veronica. Now let's take a moment to address the questions we've received from the audience. Again, please make use of the Q&A tab to ask any questions and make sure you address them to all panelists. So to begin, we have a first question, and this one is for Oscar, if you may be kind to answer it. At what stage of the project do you typically engage with the client to determine the level of risk assessments which are required?
Well, we align risk assessments required for a project as early as possible and preferably during the bidding stage. When we bid work, we want to understand what the client requirements are and what kind of effort we should do as an EPC contractor to meet those requirements. So in summary, as quickly as or as soon as possible in the project phase.
Thank you very much, Oscar. This next question is for Veronica. What size of leak hole size is considered small, medium, and large?
So the leak sizes used in risk assessments are basically aligned with the leak frequency data available that's being used in risk assessments. So as noted, to fully cover the full range of leak scenarios, typically we consider representative leaks for small, medium, and large leak and full bore rupture cases, right? So if we take, for example, IOGP leak frequency data, they have splitted the whole size bands into five different release sizes. So for example, for small, they do have 1 to 3 millimeter and 3 to 10 millimeter. For medium, they have 10 to 50 millimeter, and then for large, 50 to 150 millimeter, and then the full bore. So usually, it's either the specialist will take the largest per band or the average and midpoint. So I've seen different cases wherein it's done differently. So if we talk about medium-sized leak, I've seen 50 millimeter being used. There are cases wherein 12.5 millimeter or 30 millimeter is used. But basically, it goes back to the leak frequency data that's being used on the industry.
Thank you very much, Veronica. This next question is for Oscar. What are some ways we can address new requirements for incorporating ISD in project design lifecycle?
So as we mentioned before, you can only manage what you know. So therefore, as early as possible in a project, we want to do a hazard identification review in which we identify what are the inherent dangers or hazards associated with your process and with your project. And by knowing that early on, we can do an effort to make the system inherently safer, meaning we try to eliminate the hazards altogether, or we try to reduce inventories, we try to have less severe operating conditions, things like that. And that will help you to inherently make your plant safer. So the real key is to start early on in your project, make sure you identify your hazards, and as a team, try to identify ways to reduce the severity of the potential consequences, because that is what makes your plant inherently safer.
If I could add to that one, also what we can do on projects is if there is no separate ISD workshop required for the project, what we can do is to incorporate that on the other PHA workshops that we do. So Oscar talked about the hazard, and also even in PHAs or HAZOP, when we look at the safeguards in place, we could change our mindset to look for ways to incorporate ISD concepts first prior to thinking of incorporating, engineered solutions and stuff. But again, the timing is very important here because as we move towards the detailed design phase, it's very difficult to incorporate ISD.
Excellent. Thank you. Great questions. One more question for Oscar. Do local regulations supersede industry standards for layout requirements?
Yeah, in every project we do, we establish the hierarchy of requirements we need to comply with. Client requirements, local requirements, they're always on top of the list. So the answer is yes, local regulations where specific requirements exist supersede industry standards. Now, there are a few cases where industry standards are more stringent than local regulations. And in that case, we confirm with our client if we are to go with the industry standards. In cases where high risk is involved, most likely the more stringent requirement will be considered, but it will depend on the client risk tolerance.
Okay, thank you, Oscar. The next question is addressed to Veronica. The explosion loads from events with frequency for buildings, are those generated with special software?
Yeah, I believe this can be generated from fast risk. And then I've seen also the exceedance curve being generated using Excel file. But of course, the input data from that is considering the results of the frequency analysis and also the consequence modeling.
Thank you. One more question for Oscar. Whose responsibility is it to prepare a hazardous area classification drawing?
So within Fluor, that is done by the electrical department. So the drawing is the end result of the whole exercise. It depends a little bit on which office you're in within the company who's doing the first part of it, meaning identifying the flammable substances and determining the extent for the leak sources. Sometimes it's HSE, sometimes electrical takes care of the entire process. So that's a little dependent on the location.
Thank you. One more question for Veronica. What determines the best means of risk reduction, i.e., additional level of containment versus process design change?
It's always designing the process safely first, because if we look at I think we have like a layers of protection figure in our slide, but it's always trying to design the process safely first, and then looking at other ways to mitigate the risk using other engineered solution, because again, that's where the inherently safer design concept comes in. So that's always better in terms of reducing the risk.
Very good. Thank you, Veronica. And it looks like that is all the time we have left for questions. Thank you again, Nikhil, Oscar, and Veronica for this very informative webinar and for the time you spent today and in the preparation phase. Thank you also to our audience for attending the webinar. It has truly been a pleasure being your moderator today. Please continue to stay informed of these events by visiting the Innovation Builders page on fluor.com or following our social media channels using #InnovationBuilders. If you would like us to send you email notifications of future webinars, please email us at innovation.builders@fluor.com with opt-in in the subject line. We appreciate your attention and thank you again for dialing in today. We will send out a compiled list of the Q&As shortly, along with the notification that the webinar recording is available for replay online. If you have any questions or require additional information, please email innovation.builders@fluor.com, and someone from our team will get back to you. From all of us on the Innovation Builders team, have a safe day.